Merci beaucoup, Madame Présidente du jury. Et je suis Tosin OMOYA et je présenterai mon test sur la modélisation et évaluation de l'adaptation thermique des occupants en bâtiment. Merci beaucoup. Et je vais continuer mon présentation en anglais. Merci beaucoup. Thank you everyone for coming. I'm going to start to present in English from the moment. First of all, I'm going to take you through what I'm going to be presenting today. I'm going to be introducing this subject on thermal adaptation, and I'm going to take you through some of the background studies that I did in the process. And then those background studies led me to my research questions, which I was able to continue with which proposed to me some modeling and experimentation method, which I used, and then the results, and then some of the conclusions that I came up with. I would love to start with the issue of the climate change which the world is experiencing now, which I know every one of us have an idea of it. And this climate change we are experiencing is due to global warming, and with this global warming, we have increase in temperatures externally on the earth surface, on the water surface, and etc. And this increase in temperature is, as you can see from the screen, is actually increasing faster in the last 20 years. And projections in the next 20 years could be much more, except something is done about it. However, this global warming has caused an increase in temperatures in the outdoor conditions, and these outdoor conditions are also led to an increase in the indoor, thermal conditions. However, it is occupants that occupies these indoor places, and therefore these occupants are experiencing some kind of change in the thermal conditions in their indoor spaces. And these occupants are actually developing resilience, a way to adjust themselves or to adjust some other things to be able to live more comfortably well in their indoor environment. Now, there are a few methods which occupants have used to develop their resilience, and this method could be mitigation method, or it could be adaptive method. Now, some of the mitigation methods are by retrofitting building envelopes, modifying building envelope to adjust the thermal condition within the space. Also, we have the air conditioning systems as some of the mitigation methods, and then we have the thermal adaptation of the occupant, of the individual within the buildings. Now, this could result into the level of energy that is being consumed. It can also result into the cost of occupancy, the cost of energy. It also affects the environment, and it also have implication on the health and the well-being of the occupant. However, based on my research objective, I'll be focusing more on the human thermal adaptation. Now, to talk about the human thermal adaptation, it is quite important for me to also make some emphasis on thermal comfort, because thermal comfort is a condition of the mind that is satisfied with the thermal environment. And according to ASHRAE, it is being assessed subjectively. There are other definitions on thermal comfort, and some of the definitions shows that thermal comfort is like an intersection of physical stimuli and then cognitive systems of the human body. However, there are various factors that affect this thermal comfort, and they can be grouped into the environmental factors, which include the microclimate factors, such as the air temperature, the humidity, the air velocity, the radiant temperatures, and the clothings. And then the other factor is the physiological factors, which has to do with the human thermoregulatory system. And this system has a lot to do with convection between the body and the environment, the radiation, the sweating, diffusion from the skin surfaces, and respiratory systems of the body. We also have the psychological factors, such as the experiences the occupant has, the expectations they have, the cognitions, the habituations, their passive control, and much more. And then we have sociocultural factors, which involve cultures. It involves also the technological advancement, the standard of living, the religion in a particular place. All this affects thermal comfort. However, we can group these factors into two main branches. Now we can group the environmental factors and the physiological factors as physical thermal factors, of course, because they are objective in nature and they cannot be influenced by human opinion. Also, we can group the second part into adaptive factors, which involve the psychological factors and the sociocultural factors. Therefore, thermal perception of a person or of an occupant is being influenced by the physical and adaptive factors. In other words, physical thermal evaluation and adaptive factor react together or combine in such a way to give us the final human perception. Now, I would also like to take you through the color codes I use in my presentations. As you can see, the red colors, most of them refers to the physical thermal evaluations or factors. The yellow colors refers to most of the adaptive factors and evaluations. And then the green color refers to most of the thermal perceptions and evaluations of perceptions. Now, I would love to define adaptation. Adaptation is a reduction or the diminution in the response of an occupant in order to tend towards thermal comfort, in order to feel more comfortable. And therefore, you can see from on the screen, if you look at that point where we have the hot, which is like the physical thermal evaluations, and then the response of the person seems to be warm. The reason which most likely would have caused that is the adaptive factors, which is within the person, or the adaptive capacity of the person. And therefore, we wish to evaluate, to understand, to comprehend, and to be able to some certain extent or to a great extent, quantify this adaptive capacity of occupants. Now, to go forward, we can see that three factors are responsible. One is the physical thermal evaluation, the adaptive factors, and the human thermal perception. First of all, we want to see what other works has been done on the physical thermal evaluation. Now, the physical thermal evaluation is based on the heat balance principles. And the heat balance principle is based on the fact that the heat produced must be equal to the heat loss. So therefore, the heat produced by the body metabolism should be equal to the heat loss by the body through convection, through radiations from the surface of the skin, through skin sweating, through diffusion from the skin surface, through respiratory convection, and through respiratory evaporation. Now, a balance between these creates the thermal comfort. However, if there's a difference between them, then there's some level of discomfort based on the physiological realm or physiological evaluation. Now, a researcher called Fanga was able to process this heat balance model or heat balance principle into thermal sensational volts. And these thermal sensational volts range from -3 to +3, showing the level of sensations of the subjects or of the occupant. Now, he performed some experiments in Technical University of Denmark, where he placed some subjects in the chambers, in the climate chambers, and then he modified the temperature or the thermal conditions within there, and then he took their thermal sensational vote. He got to see that their thermal sensational vote was, he observed that this sensational vote has a relation with the heat loss from the subject's body. And therefore, he created a model called PMV, that's the predictive mean vote, which is a function of a difference between the heat produced and the heat loss from the body. However, this was a very good start or a very good move or a very good model. However, there were some few limitations to this model. Now, of course, this model functioned well with the heat balance. He tried to relate the heat balance to thermal sensational volts. However, this model didn't consider seasonal propensity, changes from like summer to winter. Of course, there are times when you have the same thermal condition or the same temperature in different seasonal, and then you feel differently and not the same. Now, this model also didn't consider a lot of psychological factors, like we mentioned before, like experiences, like experience, like habituations. It didn't consider some of this in its evaluation. Also, yes, this model was relevant for air conditioning buildings because the climate chambers was air conditioned, but it wasn't accurate, or there was some discrepancy by the field researchers who explained that it overestimated the hot temperature and underestimated the cold thermal conditions. So, and these factors that we can see that were not taken into cognizance were actually the adaptive factor. However, to improve on these models, some field researchers proposed that there should be the adaptive model. One of these researchers is the Yahoo. And Yahoo proposed a model called the adaptive predictive mean vote. Now, Yahoo conducted some experiments in the University of Chongqing in China, where students were the subjects, the students were in the classes, and he was able to take the thermal sensational vote of these students and also been able to measure the air parameters of the location or of the classes. Now, Yahoo tried to create a model that related the PMV value, that's the PMV calculations, with the thermal sensational vote of the student. And in creating this, Yahoo proposed a black box model. Now, as we know, a black box model has to do with the relationship between the input factors and the output factors. Now, the input factor is the stimuli, as we can see, delta, and the output factor is the perceived evaluation, which is APMV. Now, also, Yahoo made some postulations, and this postulation implies that within the black box, there is a physiological component and an adaptive component. And this physiological component and adaptive component, they act contrary to each other. And with that, he was able to create some mathematical expressions and some equation. Now, for the mathematical expression, Yahoo proposed that the physiological component is a function of G, which is the black box, and delta, which is the stimuli. And then that the result of that is the PMV, which is physiological. Now, the adaptive factor is a function of the black box and the psychological coefficient, K delta. And also, there is a feedback within the APMV and this. Now, he also concluded that the thermal perception will now be the difference between the physiological component and the adaptive component, as we can see on the screen. And at the end of the day, he came up with a conclusion with an equation that APMV is the function of PMV and eta being the adaptive factor. And this adaptive factor, he proposed that it was a function of the psychological coefficient K delta and the stimuli delta. He also proposed that delta, that is the stimuli, is a function of a difference between the air temperature and the neutral air temperature. Now, the neutral air temperature is the air temperature where the subject actually feels neutral. That means it doesn't feel hot or cold. And with that, it was actually quite a very good model. However, there were some few limitations I was able to note from it, that most of the measurements of and the parameters of Yahoo were actually air-related parameters. That means the air temperatures, air velocity, air humidity. And therefore, the radiant parameters were actually being estimated. And that could actually affect, to some certain extent, the accuracy of the model. Secondly, Yahoo chose to use the air parameters as the parameters for determining the stimuli. However, these stimuli have been affected with other factors, other parameters other than the air parameters, such as the radiant temperatures, such as the relative humidity, such as the air velocity. And this was not actually considered in determining the stimuli. Thirdly, from the equations of Yahoo, we're able to deduct that if we substitute, or if we have zero, if PMV is 0, then it automatically means that APMV will be 0. That means the perception, or the actual perception of the person will be 0. However, we can see that due to adaptation, when PMV is actually +1, due to adaptation, a person could tell you that he feels neutral. And also for the cold sensation, a person could tell you he feels neutral, even when the evaluations of PMV could give you slightly cold. Now, having been able to do some of this background study on these thermal evaluations, thermal comfort evaluations, I was able to come up with some research questions that were actually inclined to my research objective. One of the questions which I come up with is how can I improve the APMV model? And the next one was to how do I do a comprehensive PMV evaluation such that I can take into account more parameters that actually affect the stimuli of an occupant. And then thirdly is to actually how could I model, or how do I comprehend better or have a clearer understanding on what adaptation is. And that will be how do I do a model for the adaptive factors in the equations, and also the psychological coefficient in the equations. Now, to start with the first one, which is to improve my APMV, to improve the APMV model. Now, like we said in the previous slide, that he used the air parameters as to determine the adaptive stimuli, the stimuli of the occupant. In my case, I choose to use the operative temperature. Why? Because the operative temperature considered both the air temperature, the mean radiant temperature, and the air velocity. And with this, we have more factors which are relevant to factors that affect the stimuli. Secondly, we decide to modify the APMV-PMV relationship of the model to be able to curb the anomaly which we experienced. And it was based on the simple principle, like you can see, that APMV is a function of PMV and eta. And it's based on the same principle that the physical thermal evaluation, being PMV, reacts with contrary to the adaptive factor. Now, having done this, the next is to have a comprehensive evaluation of the PMV. And then in this case, I decided to consider all the factors possible from the convection from clothing, radiation from the clothing, sweating from the skin, diffusion from the skin, convection by respiratory system, and also evaporation or latent heat released by respiratory system of the human body. Secondly, I decided to also consider the various seasons which we experience, such as the summer, the winter, and the autumn. And then I termed it as the cold, the cool, and the hot thermal conditions which the occupant experiences, and try to consider them separately. Now, thirdly is to model the adaptation of the occupant or of the subjects. Now, to model it, I started with my proposed equation, which is the equation 1, as we can see on the screen. The second equation was to determine the PMV, which is the Fanga equation. And the third equation is to determine the heat loss, which is actually substituted in the Fanga equation, that's in the PMV equations. And then the fourth equation is the equation proposed by Yao, which is a function of the adaptive factor. And then the fifth equation is the equation I proposed based on the operative temperature parameters to determine the stimuli of the occupants or of subjects. Now, in this case, we have 5 equations, but we have 6 unknown variables. Therefore, to actually have a closure of these equations, it is important to determine the 6th equation, which is the equation of the psychological coefficient K. To do this, I came up with some operations of how to go about this. Now, the modeling and experimental protocol or operation is starting with the experimentation, okay? Experimentation protocol. And this experimenting is to experiment with some, in an enclosure, some subjects, and then to be able to determine their sensations and their perceptions and their thinking at the same time to be able to measure the physical parameters that will be involved in it. Now, with this, I'll be able to evaluate the heat loss L, and then if I can, when I evaluate the heat loss L, I was able to evaluate the PMV. And then with the questionnaire, I'll be able to get the thermal sensational vote of the subject, and then to be able to evaluate the APMV. And then we can see, based on this first equation, that with this, we'll be able to evaluate the values of the eta, which is the adaptive factor. Secondly, I'll be able to now, the next was for me to evaluate the neutral temperature. Now, this neutral temperature is a temperature when the subject feels neutral. And this point is when the APMV is 0. With that neutral temperature, I can now evaluate the thermal stimuli of the subject. And then finally, I'll be able to evaluate the psychological coefficient of the subject. So this is the flow of the operations which I wish to follow. Now, to start with the experimentation. The experimentations were, the experimental protocol or the experiments were conducted in 2 basic places. One was in the experimental cell, which we constructed, and the other was in the naturally ventilated room, or laterally ventilated room, yes. As we can see on the screen, we have this as the constructed one. We constructed it with steel surfaces, and then we were able to heat and cool from this side of the room. And then the idea was to have a set of plates that looks like the office, that can mimic the office, and then the wall is to mimic a wall that is receiving a solar gain from the outdoor environment. Now, also, this experiment was also grouped into 3 major formats, which was the cold experiment, the cool experiment, and the hot experiment. As we can see, we also have some measuring instruments which we use, the Delta Home instrument and the GraphTech instrument. The Delta Home instrument was used to measure the micro climate, such as the air temperature, the air velocity, the humidity within the room, and then the GraphTech instrument was used to determine or to measure the surface, the temperature of the surface of the walls, and then the temperatures of the clothings. Now, we can see on the screen some of the subjects in this experiment. The cool and the hot experiment were actually carried out in the experimental cell, while the cold experiment was carried out in the naturally ventilated room. Now, there were various scenarios in this experiment. There was a specific trend of scenario in this experiment, which was the same for all the experiments. It starts with the pre-experimental period, where we take the personal information of the person, including the age, the general, I'll call them the general information, the age, the sex, his countries, and etc. Now, after that period, the subject goes into the room, and then he's to wait there for about 10 minutes, and then to be able to acclimatize to the environment in the cell. And then after which, he will begin to fill the questionnaire. And then after he fills the questionnaire, he will now come out of the experimental room, and then it can be, we offered to them some interview, just a short interview, just to be able to confirm that what is actually written in the questionnaire is actually what they actually felt. Now, the questionnaire was designed to be able to find out some factors or some behaviors from the subjects. And these behaviors include the thermal perceptions of the subject, the preferred perceptions, some of the past experiences of the subjects, some of the important factors, which factor do they seem is important to them among the factors that are influencing them, and also finally to actually also check if they have some level of tolerance based on the thermal conditions. Now, to evaluate the result of the data from this experiment, the first is to evaluate the heat loss and then to be able to calculate the PMV. Now, the heat loss was evaluated. As we can see, we have various means of heat loss, like I mentioned earlier on, through convection, diffusion, and sweating and convection. Now, this graph is showing on the vertical axis the heat loss, and then on the horizontal axis the durations or the time which the subjects were in the cell. Now, the evolution we can see here is the average heat loss of all the subjects that were in the cold conditions or in the cold experiment. And we can see that the heat loss by radiation was actually the highest, and then followed by the heat loss by convection. And in this case, we were able to conclude that the heat loss by radiations and convections will actually result to about 80% of the heat loss by the body. And according to the heat balance principle, the rate of heat loss determines the level of sensation. That means these two factors will actually give a high level of sensation among, within the sensational sensation of the subject. Now, this was done for the cold condition, and in the cool condition, we have similar result of about 80% heat loss by radiation and also by convection. In the hot thermal condition, we also had similar result of about 80% heat loss by radiation and convection. However, in this case, we have more heat loss by evaporation, as you can see, that we see there was a heat loss by diffusion over there. It was actually higher than the other two slides. Now, with this, we were able to come to a good conclusion that the operative temperature will be a very significant parameters in the evaluation of thermal stimulus. Why? Because the operative temperature has similar factors or similar parameters with the convective heat loss and also with the radiant heat loss from the body. Now, having come to this point, we were able to have calculated the PMV values of the experiment. And with that, we decided to go forward in the process and in the operations, which I had earmarked. And the next was to actually evaluate the adaptive factor. And of course, we know we will have gotten the APMV through the thermal sensational vote of the student. Now we want to proceed to evaluate the adaptive factor. Now, as we were able to see in the previous equation, that the adaptive factor is a difference between the physical evaluation and the perception of the occupant or of the subject. Now, in evaluating this, we had some two different kind of subjects or two different kind of experiment. The first is the adaptive experiment. And as you can see, like on the worm, if the PMV is plus 2, and then the subject had adaptation, he might give something like plus 1, as we can see, slightly warm. Now, in this case, the adaptive factor will be greater than 1 for this adaptive subject on the hot thermal condition. And the adaptive factor for contra-adaptive experiments will be less than 0 for the contra-adaptive subject in this experiment. The same thing is applicable for the cool, where the adaptive subject, in this case, will be less than 0. The adaptive factor will be less than 0 for the adaptive subject, and then it will be greater than 0 for the contra-adaptive subject. Now, in this research, based on the fact that I'm dealing with the adaptive factor of occupant, the relevant data were that of the adaptive subjects for the both cases. Now, for the cool conditions, we can see that we have about 60% of the subjects were adaptive, of which the ones that are in red color below the 0 line, which are less than 0. For the cold subject, we have about 90% of the subjects were adaptive. Now, in this case, it was able to help us also to conclude and to be able to see that adaptive factors is not like the physical factors that are the same all the time. It has a lot to do with the choice of the person. It has a lot to do with the capacity of the person. It has a lot to do with something, information which the person has. And we can see here that the colder it is, the more they release their adaptive capacity, because more of them felt cold and they have to adapt to that environment. Now, the hot condition, we have about 40% of them were actually adaptive, and this helps us to also conclude and to be able to see that the subjects in this region are more adaptive to the cold thermal conditions than to the hot thermal conditions. Now, having been able to evaluate the adaptive factor, the next is to find a way to get to the psychological coefficient. Now, to determine the psychological coefficient, we need to first of all determine the neutral temperature, which is the operative temperature when the subjects feel neutral. In other words, that is the operative temperature when APMV is equal to 0. Now, to do this, we were able to find the average temperature of the subject, the average operative temperature of the subject when they voted 0. We can see a plot of APMV against the operative temperature. And for that, we're able to have 18 degrees. However, we still plotted for the whole subject to see the average temperature on each thermal sensational vote. And then we got a regression to see if this regression was going to pass through the 0 point. And fortunately, the regression passed through closer to the 18 degree. So for the cold condition, we have the neutral temperature of 18 degree. Also, for the cool condition, we have a neutral temperature of 21 degree, following the same method and strategy of determining the neutral temperature. And then for the hot conditions, we have the neutral temperature of 25 degree for all the subjects that participated in the hot thermal condition experiment. Now, we were able to conclude that we have 3 neutral temperatures for 3 thermal conditions. And then we were also able to see that we were able to observe that this thermal temperature increases or decreases as the outdoor temperature increases and decreases. Now, at this point, we'll be able to evaluate the neutral temperature. It means that we can go forward to evaluate the stimuli experienced by the subject. And with that, we were able to evaluate the delta, which is the physical stimuli. And then with that, of course, we've evaluated this, and then we're able to determine the psychological coefficient of the subject. Having come to this point, we decided to do some regression to find out what is the relationship between this psychological coefficient and other parameters that influences the adaptive capacity or the adaptive ability of occupants, and the subjects. Now, to do this, we plotted a regression of the psychological coefficient and the physical input factor or the stimuli. And then we were able to have a regression equation which is a function, which psychological coefficient is a function of the stimuli, and then with a slope of minus 1.4. And based on this equation, we were able to conclude that the adaptive factor for the cold thermal condition was minus 1.4. For the cool condition, we did the same regression, and then we were able to have a slope of minus 0.7, and then with that, we were able to conclude that the adaptive factor for a cool condition was minus 0.7. And then, thirdly, we did for the hot thermal conditions, and then in the hot thermal condition, the adaptive factor was 0.5. Now, with this, we were able to have our complete equation, our closure equation, which is the sixth equation. And this sixth equation is the equation for the psychological coefficient, which is a function of the stimuli delta. Now, having come to this point, we had that based on this result, we had three adaptive factors for three different thermal conditions. I would love to also make us see that these adaptive factors are sensational quantities. They are sensational quantities. And we thought of finding a way to transform these sensational quantities into some physical related quantities or physical related parameters that influences them. Just like the way we see that Fanga was able to transform the heat loss here into thermal sensational volts. In our own case, we wanted to transform thermal sensational volts into physical thermal parameters. And with that, we're able to see that the adaptive factor is a function of the psychological coefficient and the stimuli. And then we wanted to see if the psychological coefficient has a relationship with other physical parameters, such as the mean radiant temperature, the operative temperature, and other temperatures. Of course, we were able to stay with the operative temperature, which, of course, we have explained that it takes into consideration more factors than other parameters. And then, secondly, the other parameter, the other function of eta was the stimuli, or the physical input factor, which is a function of the operative temperature and the neutral temperature. And of course, the result we have here were numbers, and wanted to see if this neutral temperature has a relationship, or we want to evaluate the relationship between this neutral temperature and the outdoor temperature. Of course, in the previous slide, we were able to conclude that the neutral temperature increases as the outdoor temperature increases. Now, to deal with the first issue here, which is the psychological coefficient, we plotted a regression of the psychological coefficient and the operative temperature. And with this, we were able to have the psychological coefficient being a function of the operative temperature. In other words, if we have the value of the operative temperature, it is easier for us at this moment to be able to also calculate the psychological coefficient of the subject. And for the cool condition, we did the same thing with having a slope of minus 0.7, of which the operative temperature is a variable to the psychological coefficient. And the same thing was done for the hot condition, and we have three equations. Now, these three equations were substituted into the adaptive factor equation. Of course, this is the psychological coefficient, and we were able to have these three equations, so we decided to substitute them into these three equations we can see for the cool, cold, and for the cold, cool, and hot thermal conditions. Now, to go further, also, we went forward to determine the relationship between the neutral temperature and the outdoor temperature. As we can see, we have a regression here which shows that the neutral temperature is very related with the outdoor temperature with a slope of 0.3. And with this, we're able to also to substitute it to replace this neutral temperature here, and then we were able to have these equations for the three thermal conditions. With this, that means we'll be able to evaluate the adaptive factors when we have the values of the operative temperature and the outdoor temperatures. Now, with this result, we'll be able to expand our results, our conclusions, our closure equations, of which now we have our sixth equation being psychological coefficient, being a function of the operative temperature, the outdoor temperature, and the stimuli of the occupant. Now, having come to this point, we want to drive to some of the conclusions which we were able to extract from these results. Now, the first conclusion is we did everything possible to be able to have a comprehensive evaluations of the perception by trying to consider and by trying to take into cognizance as many factors as possible that influences this, the thermal adaptation, from the physical to the psychological to the physiological factors. Also, we can also conclude that the operative temperature is a very significant parameter in the evaluation of thermal adaptation of an occupant. Thirdly, we were able to have some specific neutral temperatures for some specific thermal conditions or some specific seasons of the year, which for the cool was 21, for the cold was 18, and then for the hot was 25. And then fourthly, we can also conclude that the physiological adaptation is also predominantly being influenced by the climate seasons, the climate variations of the occupant. In other words, their psychological reasoning is very much attached to the climate of the year, the climatic period of the year. Now, having been able to do this, we have some few limitations to the research as well as to the experiment and result. The research was actually limited to a particular location, which is in Bordeaux here. Also, it was limited to the climate variation in Bordeaux. The population type were also limited, and the building type was specific in this research or in this experiment which we conducted. Secondly, the evaluation was also limited to the adaptive subject. Of course, we wanted to resolve or evaluate adaptation, but the contra-adaptive subjects weren't considered in this evaluation. The evaluation was also limited to psychological adaptations of the subjects, of which the behavioral adaptations were not into place, were not in operation or conducted. To go further, we also have some few perspective, things that could be done in the future with respect to this work. One is to also, we can do the same model or experimentation or methodology in various locations, geographical locations that have different thermal conditions or different seasons. We can do with different kind of populations, such as the old, the younger populations separately, the male or the female separately. We can also do with different building types. In this case, we consider more of the office environment. We can consider the residential. We can consider other large building types. We can also consider these factors related to ventilations, related to the olfactory, because, of course, some of these factors also, they might not be thermal, but they also affect the comfort of an occupant, or the acoustics and the lighting. In the future, it's, we feel that this if these things if this model is tried in various places and they have very good results, we can model them into thermodynamic simulations, which are used for building designs, for the thermic designs of buildings. In this case, our reasoning is that with using this, you can actually project heat energy into buildings based on the actual perceptions of the subjects. Also, if these thermal designs are done based on this, we are projecting that there is a lot of energy savings that could be done by this method, such that we can investigate to see if the magnitude of energy being lost or being saved by this method and thermal designs. And finally, we can also look or investigate into the contra-adaptive experiment. Thank you for listening. I appreciate your listening. Thank you very much.